Okay, I guess we can get started. So we're going to do a couple different things tonight. We're going to continue on looking at groundwater flow. So up to this point in the semester, we've looked at some background about water itself, and then we spent about a month looking at the relationships between groundwater and surface water, base flow recessions, water going into the alluvial aquifers during the recharge part of the year and then draining out during the recession. And near the end of the last class, we started talking about what makes groundwater move in the subsurface. And we ended up here with the Bernoulli equation. And I'd like to spend a little more time going through this since I kind of blew through it the first time. I knew we would do that just because I wanted to give you an introduction knowing that we would come back to it. So here is the Bernoulli equation. What it gives you is the total energy per unit mass. And when we talk about mass, we're talking about kilograms. This is the sum total of the kinetic energy of the water movement and that's at V squared over 2, where V equals the velocity of groundwater. But remember, because groundwater typically moves really slow, centimeters per day, when you compare these different terms in the Bernoulli equation, because groundwater is so slow, that term is usually very small, and we can ignore it for most applications. Well, in addition to the kinetic energy, there is a potential energy term. GZ. Where G is the acceleration due to gravity. We typically measure that in meters per second squared. Z is the height above a baseline, which is usually sea level. MSL means sea level. And we measure heights in meters. And finally, a pressure term. Where P equals pressure, and rho equals density. So since we're ignoring that kinetic energy term, this energy per unit mass becomes a little simpler equation. GZ write that a little better, plus pressure over density. And now this is how mathematically we make this really easy to use, okay? So since gravity is a constant on the Earth's surface, We can divide through by gravity. And we are left with the equation that really makes this simple and what makes groundwater much easier to understand. Mathematics in groundwater can get pretty hairy, but some parts of it are actually pretty easy to deal with, and this is one place where it is. So H is what we call the total head. You can think of it as energy. It's a measurement of energy. And it consists of two different parts. This first part, Z, is what we call the elevation head. We measure that in meters. And this term here, which is called the pressure head. Now, pressure head looks a little more complicated, but if you take pressure in pascals, divide it by gravity, divide it by density, it too comes out to a really simple unit, meters. The beauty of this is that you can measure the energy of groundwater just by how high up it is in the earth. And what I'll do is I will give you next a couple of examples for you to play around with, okay? These are pretty simple. I don't think you'll have too much trouble with it. All right, any questions so far? If you do, my guess is when we go through this next part, it'll answer it for you anyway. So, all right. I want to introduce you to a term first of all. It's something called a piezometer. Sounds like some fancy schmancy piece of equipment, right? It's not. It's a well. It's a special kind of well. I'm going to show you a video here after we do this first bit of notes on well drilling. I had a student I talked to on Skype last week in this class, and she goes, "You talk about wells, but I honestly don't know what a well is. I've never seen a well. I don't know what a well is. I mean, I know what your explanation is, but I don't really know what it is." So I've got a little video showing you how they put in wells, the various parts of them, and how the whole system works. So a piezometer is what we call a fully cased well. What that means is it only has one opening. And the opening is on the bottom of the well. And the function of this well is simply to monitor groundwater. So it's used to measure the total head of a well. Now, if you get a well for drinking, it's not going to be fully cased. It'll have an opening in the bottom, like a piezometer does, but then along the sides of the well, they usually jam a piece of PVC down into your well, and the water flows into it. They just put a bunch of holes in the side of the PVC that allows water to move in more easily. Makes your well fill up a little quicker. A piezometer is different. It doesn't have all those little perforations in the side, just in the bottom, okay? And that allows the pressure at the bottom to be measured. Okay, so give me a second. I'm going to sort of draw this out. So there is a surface. I'm going to draw a couple of wells here. And these are piezometers. These piezometers are tapping into a confined aquifer. So I'm going to put in a confining layer here, most likely a shale, that allows pressure to build up in the aquifer below. In this region here, we might have our water table. Above it is the unsaturated zone, and then everything down here is saturated. All right, let me give you some bits of information here. The elevation where this well meets the Earth's surface is 110 meters ASL above sea level. This well right here has an elevation of 95 meters ASL above sea level. ES right here, this represents the Earth's surface. Now, in let's do well 1 here. You poke this well down. The only opening is right here at the bottom. And the water in that well rises to this level right here. So the water's under pressure. It's forced up into your piezometer, and it goes up to an elevation of 100 meters above sea level. So that's the elevation of the top of the water in your well. It's 100 meters above sea level. The base of your well right here is 50 meters above sea level. Okay, now for the second well. The second well comes really close to the Earth's surface, but doesn't quite reach it. We talked about different types of wells a couple weeks ago. Both of these would be flowing wells because they reach above the confining layer, or artesian wells, excuse me. Both of these are artesian wells. They reach above the confining layer, but neither are what we call flowing wells. They don't reach all the way to the Earth's surface, but pretty close. Okay? So let me give you some data for the second one. The very top of the water column rises to 92 meters above sea level. Again, this is a fully cased piezometer, so water only comes in at the opening at the bottom. The base of this well goes down to 13 meters above sea level. All right, so let's put together a little table of data that we can come up with. From this diagram that I have here. So here's our data for well 1. This is going to be our data for well 2. And we're going to measure 3 different things. We're going to measure H, which again is total head. We're going to measure E, which is the elevation head. And we're going to measure P, which is our pressure component or pressure head. Remember, all these can be measured in meters. Now, total head should be really simple. Total head is how high up the water column rises above a baseline, and we're always going to use sea level as the baseline. So for well 1, what's total head? Let me move this for you, Joseph, with this stupid thing.
It's just that bottom part.
There we go. Better?
Yeah.
All right. Oh, this is well 1. And this is well 2. Okay, let's start with well 1. What's the total head? 100 meters. What is the total head for well 2? 92 meters. Now right there, we learned some things. We know that the energy at the base of well 1 is greater than the energy at the base of well 2. Okay? So just from that, what can you tell me about water movement between the base of well 1 and the base of well 2? Things always move from high energy or high pressure to low pressure or energy. Well 1 has higher energy than well 2. So groundwater is generally going to flow in that direction. Total head tells you that. Okay, elevation head. The elevation head is the height that water rises up within the piezometer, within the well. So it's the height of the water column above the base of the well. So how high is the water column above the base of well 1? Yeah, you can think of it as the filled height of the piezometer. So the base is 50 meters, right? Top of the column is 100 meters. So how much of it is filled? Should be 50 meters. So that's the elevation component. I just said that really wrong. It's been a long day. Let me start that over, okay? I just gave you a great definition for pressure head, okay? You guys just gave me the pressure head. So pressure head is how high pressure is pushing water up into your piezometer. As it turns out, it is actually 50 meters, like you said. Okay, so I'm just going to move that over to the pressure and get rid of this. What's the pressure head in well 2? It's just the column of water in the piezometer. 79. The top is 92, the base is 13. The difference between those two is 79. So it rises up 79 meters in the well because of pressure. Now, let me give you the proper definition for elevation head. It is the elevation of the base of the well above sea level. So for well 1, what is it? 50. You actually had it right with the wrong reasoning earlier. thanks to me. 50. What's the elevation head for well 2? 13. The base of the well is 13 meters above sea level. Okay? All right, let me give you an example and you can try it on your own. Everybody good on this? All right, so let me write out an example here. I'll write it and then we'll read through it. Okay. So first thing I want you to do is draw a little diagram that shows kind of the setup of this example. So we have 2 points in an aquifer, in a confined aquifer. Point 1 is 100 meters below sea level. So it's kind of a deep well. This is probably an area near the coastline. So the base of well 1 is 100 meters below sea level. The surface is 150 meters above sea level. The water in well 1 rises to within 20 meters of the surface. So you should be able to kind of put some numbers to all this. For the second point in the confined aquifer, the surface again is 150 meters above sea level. The base of the piezometer is only 50 meters below sea level. And the water in this well rises to within 25 meters of the surface. So what I want you to do is sort of draw this out so that you have it conceptually, and then figure out the total head, the energy head, and the pressure head for each of these wells. So I'll give you a little time to work on this. After you've finished, just shoot your hand up, and once everybody's done, we'll go through it. How are you guys doing? Need more time? A little more? Okay. Definitely don't want to rush it. I want you to learn by making mistakes and working through the problems. So if you're making mistakes, no worries, that's how you learn. Still need more time, or are you guys good? Okay, so there's a couple things we know about the problem, right? There's a confining layer. I didn't tell you where it was. I didn't tell you what angle it was. I didn't give you a lot of information. I'm just going to keep it simple. Since both of these wells tap into a confined aquifer, we just know the confining layer is above the base of those wells, okay? So if you had it at an angle, that's cool. If you had it horizontal, that's cool. You just need a confining layer in there. What do we know about the elevation of the Earth's surface?
150 meters above the sea level.
It is, what did I say, 150 meters? 150 meters above sea level, okay? So that's the surface. What do we know about well 1? Where's the bottom of well 1? Right down here. Point 1. What information did I give you about point 1? 100 meters below sea level, okay? So this is 100 meters BSL, below sea level. Okay, well 2, we said had the same surface level, right? 150 meters. What about the base of well 2? 50 meters below sea level. So if you think about that, if that's 100 meters, then this would probably be about 0 meters. This would be, I haven't drawn this to scale, obviously. Let me move this so it's a little better. Let's make that about sea level. This would be 50 meters below sea level. We'll just call it minus 50. And then this is down 100 meters, right? What do we say about where the water rose in well 1?
It must reach within 20 meters of the surface.
Okay, so it goes, if you went down from the surface, you'd go down 20 meters and you would reach water. Okay, so the water is going to rise to about there. And what about well 2?
Within 25.
Within 25. Okay, so now actually we have all the information we need to kind of fill out the table here. So let me make a little table. So this is going to be well 1. It's going to be well 2. We're going to have total head, elevation head, and pressure. Total head is the elevation of the top of the water surface relative to sea level. So what's it going to be for well 1? What'd you get? 130. Yeah, it's the elevation of this point right here. So if the surface is 150, and that's 20 meters down, this has to be 130 meters. Okay? So this is 130 meters. What about well 2?
125.
Same reasoning, 125 meters. Surface is 150. It's down 25 meters, so this has to be at 125 meters. Well 1 has more energy than well 2. Now the elevation head, and I intentionally did this funky below sea level stuff just to show you that it works above and below. Elevation head is the elevation at the base of the well. What is the elevation relative to sea level of the base of well 1? Negative 100. Always keep our units, meters. What about well 2? It's down 50 meters, right? So the pressure head then, I can mark this down, negative 100 meters is negative 50 meters. The pressure head then is just the height of the water column in the piezometer. So, for well 1, what's the height of that water column? 230. You've got 130 meters above sea level, the extra 100 meters below sea level. So this is 230 meters. For well 1, we have 50 meters below sea level, plus 125 meters above sea level. Add those two together, and you should get 175 meters. Okay? Any questions on those? Okay, so remember, let me just write this out so that you have it nice and clear in your notes. The elevation head, sometimes it's referred to as E, or sometimes H sub E. Let me redo that. That doesn't look like anything. This is the elevation relative to sea level. At the base of the piezometer. And again, a piezometer is just a well with one opening at the bottom. pressure head. Sometimes written as P or H sub P. This is simply the height of the water column within the piezometer. And finally, total head. Sometimes it's written with a little h, sometimes h sub t. From this point forward, I'm going to try to be consistent and use h with the subscripts there, h sub e, h sub p, h sub t. Total head. Is the elevation of the top of the water column relative to sea level. Okay.
What's the sub for the total head? H sub what?
Right there, T.
H sub T.
Yep. H sub E, H sub P, and H sub T. All right, let's beat this dead horse. I'll give you one more example, and hopefully you guys will all have this here. Let me give you some data. So the following data are from 3 piezometers located within a few meters of one another. Basically, the driller went out there, stuck a hole in the ground, stuck another hole just a few feet away, and stuck another hole a few feet away from that one. But they all went to different depths. So what you do that for is to see how the pressure levels change in the aquifer at different depths. It gives you an idea of how the water might be moving within that aquifer. So let me just sort of write out the data here. We're going to call them well A, well B, well C, I'm going to give you some data. So we're going to have the surface elevation, the distance from the surface down to the base of those wells. And let me write this better. And this is distance from surface to the top of the water column. And then I'm just going to fill in the data for you here. Not surprising, they all have the same surface elevation because they're basically right next to one another. So this first one, well A, the driller drilled down 150 meters from the surface. Sunk a bunch of PVC down to that lowest level and made this into a piezometer. The second one, he only drilled down 100 meters, did the same thing. And the third one, the driller drilled down 75 meters. So these all went to different depths, even though they're very close to one another. And in all cases, water rose up into the piezometer, meaning it was under pressure. So in this first one, the distance from the surface down to the top of the water is 80 meters. In the next one, it was 77 meters. And in the third one, it was 60 meters. So again, I want you to do two things. Draw this out. Again, assume it's a confined aquifer. For each of these wells, I want you to give the total head, the elevation head, and the pressure head for each. Okay, you guys need a little more time, or are you good? All right, let's look at what information I gave you. So let's look at well A. We said the surface elevation was 225 meters above sea level, okay? And for well A, how far down did they drill from the surface? 150 meters. So this distance right here is 150 meters. So the question becomes then, what is the elevation at the base of the well? So we have 75 meters. We have 225 surface elevation minus 150 meters down gives us an elevation at the base of that of 75 meters. Okay? Now for well A, how far down from the surface do you have to go to hit water? 80 meters. So it looks like a little over halfway here. So that means that the water moved up to this level right here. And that this was 80 meters down from the surface. So what's the elevation of the water level? So you have 225 at the top, right? And it's 80 meters down. So you're subtracting 80. So you should get 145. Okay, let's look at our three terms that I wanted you to tell me about. Total head. Just what is the definition of total head again? It's just simply the level, the elevation that the water rises to, right? What's the elevation that the water rises to for well A? 145 meters. I'll put my meters there. So 145 meters is the total head. And total head consists of the elevation head plus the pressure head. Elevation head is what? Yeah, it's the elevation at the base of the well, which is right here, which is 75. What's the pressure head? Pressure head is 70, or it's basically this level right here, the height of the column of water in the piezometer. So 75 plus 70 equals 145. So your pressure head plus your elevation head should always equal your total head. All right, what did we say for well B? How far down did the driller drill? 100 meters. So if it's 200 meters at the top and you drill down 100 meters, you should get an elevation at the base of the well of 125 meters. How far down from the surface is the water? 77 meters. So 77 meters. That's where the water rises up to. What is that elevation? Oh, wrong one. Let's see. What is that elevation at the top of the water column? 225 minus 77. I think if I do math right, I get what Joseph gets, and it's 148 meters. Okay, so what's the total head? 148 meters. What's the elevation head? 125. It's the elevation of the base of the well. The difference between those two is going to be the pressure head. What do you get for that? 23. Remember, the pressure head plus the elevation head should equal the total head. Okay, finally, let's go to the last one. How far down did the driller drill? 75 meters. So if it's 225 meters at the top and you drill down 75, you should get 150 meters above sea level for the base of your well. How far down from the surface is the water level? 60 meters. So that's to the top of the water column. So the elevation at the top of the water column is 60 meters down from the 225 meter surface. That should be 165. So what's the total head? 165. What's the elevation head? Elevation at the base of the well? 150. And what's the pressure head? 15. Okay. Now, we haven't done anything with this info yet. We're just sort of going through the background. We'll try to do some stuff when we come back from spring break. But where do these numbers come from? Okay, the distance they get to the base of the well, the driller knows. Okay, I'm going to show you a video after break, and they know exactly how far down their drill bit is going and how far down they're jamming their PVC. So the driller can tell you the depth, and then water rises up in your well. Okay, how can you get the depth from the surface to the water? Because this first one, that's 80 meters down, right? That's almost a football field down. How do you measure that? Well, it's actually really easy. We have these little contraptions. It's basically a tape measure with a metal weight on the end. And on the tape are two wires that run all the way down right to the metal end, but they don't connect, okay? And at the very top of the tape, those two wires are connected by a battery. So the battery is trying to make a circuit, but it can't make a circuit because the base of the tape, those wires aren't connected. But when you drop it down and you hit water, because water conducts electricity, it completes the circuit. So you feed this tape down this hole, and it goes down, 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 and when it hits the water, it completes the circuit, and the little battery is hooked up to a little beeper, and it makes a beep. And then you just look at your tape measure, and it says 80 meters, or 60 meters, or 70 meters. Really simple, sweet little contraption. So all it's doing is using the water to complete the circuit to make a beep. And then you know that that's the depth to the water in your well. Okay, so let's take a break, and when we come back, I'll show you a video on drilling a well, and I'll give you